Today is Friday, so we've got to talk about something a little bit different. Kind of a palate cleanser, keep our minds off of our current work, think about something else for a little while so that we can take our current work and put it on the back burner and let our subconscious work on it for a while. So today is a good time to talk about length, area, and volume. This is going to be moving forward once we get past some derivative stuff and start working in some integral stuff. This is where things are headed. So length, area, and volume are all things that we use to take all words that we describe to take up space. One-dimensional space, two-dimensional space, and three-dimensional space. We could keep going, but these are the three that we work with the most. And we want to think about how this is constructed, because we want to go back to the beginning and think about how these things are constructed, how these things are defined, because most of the math, even when we're pushing forward into calculus and stuff, is based on old stuff. We're just modifying our old ideas to fit with the new things that we want to do. So let's think about how we take a point, go up to a one-dimensional length, to a two-dimensional area, to a three-dimensional volume. So here's how I want to think about it. We start off with a point. A point is zero dimension, takes up no space. That's the important thing about a point. We represent it with this big gigantic dot, but we understand that we're talking about a single point that takes up no space. One level up from this, we take that dot, and now we have that point, that zero-dimensional point, and we allow ourselves one dimension. We allow ourselves one dimension, like an x-axis. If we want to be analytical about it, we build an x-axis. Now, when we take up space, we could take up an interval, and that interval will have a length. How far is it from one point to the other? So we're just going to grab this point and drag it along our dimension. We just grab the point and we drag it along our dimension into a length. Drag the point along our dimension into a length. We drag the point along our one dimension into an interval. The space that the interval takes up is its length. Then we just repeat this game by adding more dimensions. So the next one up will be an area. Now we're going to allow ourselves a second dimension. We're going to take our area and we're just going to drag it into our second dimension, maintaining its length and just drag it into our second dimension for a while. So now we're going to take our interval and drag it into our second dimension, and we'll have a two-dimensional area. So now I've got a two-dimensional thing. So we're just going to drag our interval along the second dimension, along our second dimension, into a rectangle with an area. Our interval, or our rectangle, is just two intervals. To find the area, we just multiply the length times the width. Area is just length times width. Then we just repeat this process. I take the area that we have now and we drag it into a third dimension. Now we're going to allow ourselves a third dimension. We just take that area and drag it in along a third axis into a volume. So I'm going to take my area, which was we took our point, dragged it along one interval into a length, took that interval, or dragged along one axis into a length, took that interval, dragged it along a second axis into a rectangle to produce an area. And now we're just going to grab this rectangle and drag it along a third axis to produce a solid. Gone too far. I didn't want to do two because I needed the height. Here's our original point that got dragged through dragged into an interval. So now we're producing this three-dimensional solid by grabbing our two-dimensional area and using just taking it in a direction that we haven't used before. When I start off, I introduce left to right, then I introduce up and down. Now I'm introducing forward and backward. And we're producing this three-dimensional thing, where we just drag our rectangle along our third dimension into a solid with volume. Take our area, our rectangle that had area, we drag it into a third dimension that we haven't used before, and that produces a solid, a three-dimensional solid with volume. And we get the volume just by multiplying our three lengths. So our volume is length times width times the height. One thing that will be useful for our framing is we could look at that length times width and recognize that that's just area. So what we're doing is we're taking this area and multiplying it by the height. So we can say the volume is just our cross-sectional area multiplied by the height. We could take this further, but it becomes kind of messy to draw. Already I've had to squash one dimension out of our representation because I'm drawing on flat paper, flat plastic. So already we've squashed one dimension out of our representation. But we're so good at fooling ourselves into thinking that things are three-dimensional that we can see that this is a three-dimensional thing. It would be hard to take this further because it's hard for us to picture things in four dimensions. But if I wanted to go one step further, I would just have to take this volume, take this solid, and drag it along an axis that we haven't used yet. Right now, in our minds, we're out of dimensions. I've got left and right, then I used up and down, I've used forward and backwards. I'm kind of out of space in my mind to picture it. But I could just drag this out, drag each of these points into some fourth dimension. The usual way to draw this is to take these 8 corners and just expand them out. So the usual way to do this, we could use a fourth dimension of time, but So we could, if I had animation, morph this into a fourth dimension and have it change through time, but that would just be us representing distance with time. So what's the fourth dimension that when it's in meters? We could picture it by using time. If we were better at color, we could picture it using color gradient, but I don't have those available to me, right? Also, we don't want to say something like the fourth dimension is time, because the fourth dimension is whatever we need it to be at the time, at the moment. And I need it right now to be meters. We could have an infinite amount of dimensions. There are infinite dimensional vector spaces. But the traditional way of taking this into a 4 dimensions to a 4-dimensional hypersolid is just to grab each of our corners I can't have extra spots. I will get lost. To grab each of our corners, I'm not sure where I'm going to put them. Keep track of where everything was. Our left to right, that's our original length. Here's where it got dragged in our second dimension move. And then here are the two that got dragged into our third dimensional move. There's our second dimension making an area. Here's our third dimension making a volume. So I just need to take these 8 corners and then drag them through our fourth dimension. And it's gonna be hard to find a place to put it. We're just gonna drag it into a fourth dimension. The typical way we represent this, I did that badly, is to essentially draw this inside of another cube. I don't know why I'm thinking about this so much. It's gonna look terrible. But each of these points is just got to head off to, so did I get them all? 1, 2, 3, 4. Okay. Each of these points is going to be dragged out into a fourth dimension. And the typical way to do it is essentially just draw them a little bit further away and think about it expanding out into our fourth dimension. Now, this is going to look really bad, mainly because this cube, this rectangular solid, has squashed out 1 dimension in its representation. It's only going to get worse because now I've squashed out 2 dimensions. I've got a 2-dimensional representation of a 4-dimensional thing. So each of these points just gets dragged out. And so here would be our original length dragged into its fourth dimensional location. Here would be our original interval dragged into its fourth dimension. Let's see, here's another one that was left to right. Here's another one that was left to right. Then I had my up and down, and my up and down, and my up and down. back, front to back, front to back, and front to back. And then you get the tesseract from Marvel. So now we have to fight over it. Local needs to show up and steal my notes. Question? Yeah, so hyper volume. We just call them hyper for extra. So we would say it's 4-dimensional volume, 4-dimensional hyper volume. But if I wanted to calculate this hyper volume, it's 4 dimensions. All we did was drag our rectangular solid into a dimension that we haven't used yet. We don't have words for it because I got left, right, up and down, front, back, this way and that. So it's just this way and that. But our volume, I'll call it big H for hypervolume, is just going to be length times width times height times, I don't know what we call it, depth. All those purple segments have to have the same depth. They're all at the same depth. It just looks weird. It's distorted because I squashed out 2 dimensions. In addition, notice that the first 3 factors of our hypervolume are just length times width times height. So we just took the volume and multiplied it by how far we shifted it through the other dimension. I wanted a more Street Fighter naming convention. I would have been like, all, this is volume turbo. But that's because Street Fighter came from the 80s and everything was turbo in the 80s.
Hey, Professor.
Yes.
Wouldn't 5th dimension be time travel?
No, I could have another distance if I want. I just have to take this, extend it through another, take all those, because I've got 16 vertices now. Got 16 vertices now. I just have to pull them through a 5th dimension that I haven't used, and I have meters for the 5th. Or I could watch it change through time, and I could have meters to the 4th times seconds. But we always want available. This is just location. We could always just think about describing this as location. What we need more functionally is just how we deal with all these extra things. What it represents is secondary to how we deal with what we're trying to with how our calculations are supposed to go. Remember, this is math class. We picture things when it helps us picture things, when it helps us understand the mechanics of what's going on. But our job is to work the mechanics out and deal with the math of the stuff that's happening. which I think is there's that Einstein quote, says, do not concern yourself with your difficulties in mathematics. I assure you mine are greater still. Which we like to take as an inspirational quote to say, oh, Einstein wasn't good at math. I assure you Einstein was excellent at math. Einstein was perfectly great at math. The context for the quote was they're doing physics that are so advanced that the math hadn't caught up yet. And so he's like, don't worry about the stuff that you have to worry about in math. At least we know this. I have to deal with math that we're just now inventing as we go. So it's kind of a dick quote. So really, if you translate it to modern parlance, it'd be kind of like, oh, you think you got problems? I say, oh, come on, Al. This is not the misery Olympics here. So I wanted to go over this, not because I think we don't understand how length, area, and volume works, but I want to imagine length, area, and volume as being just an extension. I want to think of one as an extension of the other. I want to think about area as just grabbing this length and stretching it into a width. I want to think about volume as grabbing this area and stretching it into a height. That's the way that we want to think about this, because one of the things that we have to do in calculus, one of the things that happens in calculus is that we want to do multiplication. We want to do multiplication where one of the variables is continuously, one of the factors is continuously variable. So in calculus, our multiplication evolves, so that our multiplication is going to involve a factor that is continuously variable. So in calculus, we start doing integration. And integration is multiplication where one of the factors is continuously variable. This is why we want to start building calculus, because integration is multiplication with a continuously variable factor. One of the factors is continuously variable. What this means is that integration represents addition, because addition is what we do when we can't do multiplication because things are variable. The variable part means that integration is addition. So the variable part means integration is addition. That's what we do when we have variable. We don't get to multiply. We got to add. The continuously is where calculus comes into it. This is where we build our Riemann sums. What we're doing is approximating the continuous with the discrete. The problem with continuous addition over a continuum is that there's nowhere to put the plus signs. So we model that continuum with a discrete set so we can put plus signs in there. And then we just use more plus signs. We're using the discrete to model the continuous. We're using a discrete sum to model a continuous sum. Here's our relationship between addition and multiplication. If I have 5 plus 5 plus 5, we get to say 3 times 5. We get to use multiplication. When everything is the same, when all the terms are the same, we get to take that term and use it as a factor. When the terms are the same, we get to multiply. If the terms are different, then we don't get to multiply. We're stuck with addition. When the terms are different, we are stuck with addition. If we visualize this in terms of area, if I've got a height of 5 and I use that for 3 units, I get to multiply because my length or my length is constant throughout the width. Our length is constant. So we get to multiply. However, if we have different values for our length, our length is variable. So we use addition. We look at those each individual segment from 0 to 1, from 1 to 2, and from 2 to 3. The length is constant on those intervals. So the length is variable, but the length is constant on intervals. First complication, old complication. If everything's the same, we get to multiply. If things are variable, then we're stuck with addition. We get to multiply on parts in bits. We get to multiply in bits because the length is constant on these intervals. You got all these flat places. It's constant on intervals. The next complication is that we make the length continuously variable. Our most complicated version, the length is continuously variable. We can't just multiply on intervals because it's changing. It's not constant on any interval. There's nowhere to put the plus sign. So we look at the three things that we normally do when we get stuck. Multiply by 1, add 0, or drop back to an easier problem. And that's exactly what we do. That's the idea behind calculus. We say, well, this is a problem. The length is continuously variable. I can't use addition because there's nowhere to put the plus sign. And so the idea is make a place to put the plus sign. Create a model where you can do what you want to do. Create a model where you can do what you want to do. How's everybody okay? Just do a different problem. Do a problem that you do know how to do. Take a problem that you've done before and do that. The trick is identifying when you have a new problem, what problem does this look like? What can I get away with? One of my favorite examples of this is Feynman's technique for integration. The sneaky thing about integration, as you saw in Calc 2, was that there are some functions that don't have nice integrals. However, when you're going the other direction with derivatives, there is not a function that I can cobble together that you can't differentiate because you've got product rule and quotient rule and chain rule. So with time and proper motivation, I can't put together a function that you can't find the derivative of it. No question. Just you have all the tools you need for any derivative. I mean, so long as it's differentiable. If I put corners in something, then of course we'll have problems. But I'm just putting stuff together, no problem. And what Feynman's technique does is say, well, we can't integrate this thing. I don't know what to do to integrate this thing. So here's what I'm going to do. I'm going to differentiate it on the inside. And I can say this now because it involves partial derivatives, and y'all are skilled with partial derivatives now. If there's only one variable, you just introduce another variable and differentiate with respect to that. And then see what happens. Any questions? So this goes back to the beginning that we were, at least the beginning of today, where we're talking about length, area, and volume. Because what I want to do is I want to take this point and drag it along one dimension into an interval. And then we're going to take this interval and then drag it into a second dimension to produce an area. Now, the reason that we got away with multiplication is that the length stayed the same that whole process. The length was constant throughout that whole width, so I got to multiply. What calculus says, what if while we're dragging this length into our second dimension, it just continuously changes its length? The length continuously changes. Then this multiplication turns to integration, because integration is what we do when we want to multiply, but one of our factors is continuously variable. Then we just have to adapt that into different scenarios. What we did is take the cross-sectional area and stretch it into a third dimension. And we saw we could even do some of this in Calc 2, but we had to have some very contrived problems. It's like, well, the area is going to be continuously variable as we drag it through the width. We had to be very careful because we only got one variable to work with. So if you recall, when we were doing volume problems in Calc 2, the shape always had to be the same, but its size could change. So if I've got this cross-sectional area and it's a rectangle, I had to be able to say length times width at every point along the height. Because I only have one variable to work with, I had to be able to write that rectangular area in terms of the height. So now that we're in Calc 3 and we have better technology, I can say, what if this area is different? What if it's not always a rectangle? What if it's not always a circle? What if it's not always, I don't know, what are the other ones that we used? Any questions? This game is so much harder when you restrict yourself to one variable because everything has to be contrived so that we can write our functions in terms of one variable. Now that we've got two variables, that is off. So our lives are so much easier. Mechanically, I guess they're more difficult because we got to learn how to do the mechanics on functions of more than one variable, but at least the framing will be a little easier. Any questions? On Monday, we snap back to optimization with constrained optimization and Lagrange multipliers. This was a Friday. Like, oh, well, we don't have any homework on this yet, so I'm not going to think about it. But secretly, you are going to think about it. I don't know why Inception was such a big deal. It's like, oh, we can't make people have ideas. Like, well, yeah, you can. You just bring it the fuck up in conversation. It's like, oh, yeah, hey, taking up space, length, area, volume. It's like, oh, I'm not going to think about this. I'm sorry, but you can't not think about it. In fact, not actively thinking about it is exactly what I want you to do. So if you want to defy me, if you want to rebel against your instructor, actively think about taking up space, length, area, and volume. That's going to do it for today. I'll see you all. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing. Inception and the top's still spinning.